Yes, yes, we can. Thank you.
Okay, thank you very much, everyone. Welcome to my presentation. Let me see. Okay, I'm Shahab Ardalan from Ayar Labs, and the talk is about the optical chiplet or chiplet optics. In Ayar Lab, we are building optical chiplet, or as we say, we design and sell optical I/O. I think most of you are expert in the area of the multi-die module, and you know the benefit for going to this ecosystem or multi-die solution. But in the current market, I think we do have different products already out using chiplet technology. I think Intel, AMD, Xilinx, and other few companies are doing it. But in very brief, what are the benefits that we are getting for doing a multi-die or chiplet approach is, first of all, we can actually use chips within the different technology and with the different functionalities, for example, memory or CPU and I/O, and combine them together. And each die can be actually in a different process nodes and technology, which that process node could be optimized for the functionality or availability of that IP. Of course, yield is going to be better because we're going to reduce the size of the chip, and higher yield usually better price tag. For optical interface specifically, to be in the chiplet ecosystem, we need to be more like electronics, which is not easy, but I will explain in details what do I mean by being more similar to electronics in later slides. Okay, if we just want to look at the in-package optics and why do we need to go for that is, if we look at the package performance, it's right now pin limited. Basically, the speed of package I/O is pin limited, and also the amount of power that we are burning to go off chip is actually going crazy, and it's beyond the level that we can manage. In a heterogeneous data center workload, also we need some new architecture, which is the mixing of the CPU, GPU, FPGA, different accelerators, memory, and those kind of things, which again, they need to get combined together and go to the a better architecture, and therefore they need a communication between each die. If we just look at the comparison between in-package and off-board, we see something, a huge penalty that we have to pay if we want to go and make the communication basically out of the board or even on board, compared to do the communication in-package. That actually brings another motivation should we have a co-package optic or in-package optic communication. We see actually some kind of 4-order magnitude in this slide in terms of the figure of merit when we go from the in-package to off-package, basically, off-board. By moving basically chiplets to, optics to a chiplet environment, what do I mean by that? Let me just clear out what is actually going on. We used to have, and still we are using this approach at the left side top, which is pluggable optics. When you do have your ASIC or switch or chip that you have here in the board, and the optics is going to be right at the edge, fiber is going to get connected to it, get converted from the optics to electronics in the orange chip that I have here, get routed in electronic domain through the board, and then goes to the ASIC IC or switch chip that we have. Also, we do have an onboard optics, which the photonics chip, which the orange one, is going to get closer to the ASIC side, and you do the transformation more on the optics side to the edge of the board or chassis. Co-package optics is asking actually for a solution to bring the orange one, which is the photonics one, in the same package as ASIC and make the connection basically through the substrate package or package substrate that we have. How we can do that? There are at least 4 different approaches that people are taking. One is actually having a kind of XSR link between these 2 dies, and then having an XSR over there. Again, optics is going to be on the orange, and we develop TIA and driver in different package. We do 3D integration and 2.5D integration between XSR and optics, and then basically connection another level of the 2.5D integration with the ASIC chip. This is pretty complex, a lot of stacking on top and connection. Another option is actually to get rid of this XSR and just drive the optics with the TIA driver again in a separate dies and combine them on top of that, or 3D stack or something. Another option is if we can actually do the TIA and driver included in the optical chips, if we have that process, then we can actually drive it directly with XSR. Or in another fashion, if we can actually go furthermore and have optics, TIA and driver, and retimer, or a kind of die-to-die interface. For example, in this chip that I'm mentioning, we're going to use AIB, which is a parallel bus, and we're going to actually go with the EMIB bridge and connect ASIC to the optics. This is actually the goal for Ayar Lab products, as we call it actually TeraPHY. Let's go actually to see if we want to build TeraPHY as a chiplet, what do we need? This is the area that I mentioned before. We need to be more similar to the electronics. First of all, to enable these things, to enable TeraPHY, we need to have actually dense optics, such as micro ring modulator. We cannot use Mach Zehnder, they are so bulky. And then we need to actually be monolithic with the electronics, because we are implementing different things such as TIA, driver, full SerDes, everything. And they have to actually get implemented in the same process as photonics process. And that process needs to be actually in high volume manufacturable quality. On top of that, we need to actually have advanced packaging, because right now the fiber is actually coming directly to our package. And since we are actually increasing the data rate by having a multi-wavelength approach, we need to actually have a good source of the laser, which gives us a multi-length waveform laser. And all this thing needs to be in the ecosystem and actually a kind of a standard around it, which we already started and we are doing. This is after developing all those steps. This is what we so far achieved in Ayar Labs. We have a monolithic CMOS integrated silicon photonics, as we call it, TeraPHY, the red one here. The laser source is going to be outside the environment of the chip, which could be on the board. The laser is coming to the TeraPHY. TeraPHY with the SOC, could be ASIC, could be CPU, GPU, anything, is going to get packaged in the 2.5D architecture or EMIB approach, anything, and enables actually the optical communication to the outside. And the fiber is going to come directly actually to the packaged SOC. This is actually a good solution for us. We are using EMIB, which is a parallel high-speed bus here, over a silicon interposer. And again, as I mentioned, the laser is going to be outside, it's going to be in the cool environment, and yield is going to be higher. What we can achieve with this, with each of these TeraPHY, we can actually go up to the 2.5 terabit per second, and the reach is going to be around 2 kilometers, which gives us 1,000 more bandwidth and 1/10 of the power that we're going to have. And of course, low latency. This is basically a snapshot from the chip, what is inside the TeraPHY from Ayar Lab. At the left side, we have an AIB, which is the die-to-die link that we have. And then we have a crossbar here to convert it to the internal serial speed that we need. We have a 10 macros of the TX and RX, and each side of this macro, we have 8 TX and RX for each wavelength, basically. And then at the right side, you see the huge area for fiber attached, which fiber comes actually directly here. With this configuration, we can actually achieve something between 1 to 2.5 terabit per second. The modulation that we use is NRZ, not PAM4, therefore no FEC is required. Latency is so low. And in our roadmap, actually, we show that we can actually go through up to the 25 terabit per second per PHY. This is a close-up from the wafer that we have. I'm going to go a little bit faster for the time, but you see this is a die from the front and basically back of the chip, back of the die. We are using mixed pitch bump. This is the micro bump area here, which is used for AIB. At the right side is for the power and other stuff from our block. And you see AIB here, crossbar, and the 10 macros that we have here, and the fiber is going to get attached here. In each of those 10 macro, in each macros, we're going to see actually the 2 PLLs, a clock distribution, and 8 pairs of the TX and RX. And inside of each TRX, we do see that the full RX TIA equalizer, clock distribution link here with the PI, and also at the TX side is going to be eye monitor, heater, driver, and driver. I just want to mention these 3 dots or 2 small dots that you see here. These are basically our modulator and photodetector in the ring resonator architecture. This is everything get packaged. This is a sample chip that we did with our partner as Intel. The chip in the middle is going to be Intel FPGA, 2 TeraPHY sitting left side as a chiplet. And here is actually the picture for full package FPGA with the TeraPHY IO. So far, these are the things that we do have available for demonstration. And if you are interested to get basically the kit for evaluation, feel free to contact me over the email. We do have a single die package demonstration, which is only TeraPHY solution communication to another TeraPHY. This is the multi-chip package, which is there is a FPGA of the Intel here and 2 TeraPHY. And also we do have our laser source to provide the dense laser for different multi-waveform. This is a 32 different eye diagrams that we have for the just 4 macros, and each macro is actually using 8 lambda at 25 gig, which we demo 800 gigabit per second on the single die package. And we have the same approach, same demonstration for multi-chip package with the FPGA from Intel and the laser source from Ayar lab, which is SuperNova. And the TeraPHY is already 2 TeraPHYs inside this package with the FPGA. Just as a conclusion, chip-to-chip communications requires photonics to overcome I/O bottlenecks. This is something that we believe and we should go for it. Emerging chiplet ecosystem offers opportunity for monolithic in-package optics, and in-package optics fundamentally breaks the traditional bandwidth distance trade-offs that we have, and we are supporting new high-performance computer architectures. Call to action, I think if you're interested to understand what's going on the BO and participate in the standard definition, please contact BOPI. Also, there is a CES chip plan, which Suresh before me just talked about. Again, contact BOPI. Meanwhile, also, we are working on to gather some information about the different die-to-die PHY available on the market, which we're going to have a presentation on it on Wednesday. But if you do own a die-to-die PHY and you want to get listed on that comprehensive comparison list that we have, please contact me or BOPI about that.
Thanks, Shab. By the way, there are no presentations tomorrow. It will be on Thursday.
Sorry.
So
Yeah.
I just wanted to make sure that the audience understood that,
Yeah,
in observance of Veterans Day, we're not having any sessions tomorrow. So thank you very much. And I think that